Okay, so hi everybody, welcome back. So we finally have reached the end of the semester, and this is actually going to be our very last video. So I think it's a little bit too late in the game at this point to try to cover any new material. So instead what we're going to do is a recap of the entire course. So we're going to go through all of the material that was covered this semester, starting from the very beginning, and just do an overview of all the important concepts, the topics that we covered, and the equations that you need to know going into the final exam. So because there is so much to cover, I'm not really going to be able to go into a whole lot of detail into any one of these topics. Instead, again, it's just sort of an overview. So we won't be going through any example problems or anything like that. However, remember that you do have a review packet for the final exam with a bunch of different problems. So every time we hit on a topic in this video, think of that as a jumping off point to go do a problem from the review packet. And again, that will help you study for the final exam. So let's get into it. So the first chapter that we covered this semester was chapter 7, which deals with work and energy. So we'll start by defining some basic terms. Remember, work is a transfer of energy via a force. So here's the classic example we use when we first define work. We think about a box being pulled across the floor using a rope, which can be at any angle that you like. So this would be the force, and the displacement doesn't necessarily have to be in the same direction. So the box can be moving in a different direction than that force that you're applying. But of course, the idea is when you apply this force, you transfer some energy to the box. You give it some kinetic energy, in fact, by making it move faster. So that's the idea behind work. So again, the force and the displacement aren't necessarily going to be in the same direction. There can be some arbitrary angle between them, which we call phi. So how do we calculate the work then? Well, there's some different formulas that we've seen, but at a basic level, it's just force times the distance that we move times cosine of the angle phi. And there's an equivalent way of writing this in terms of a dot product, which is the force vector now dotted with the displacement vector. These are just saying the same thing. Now, this only works, by the way, if we have a constant force. So the assumption, if you use either of these formulas, is that the force in question is not changing. So if you have a variable force that is changing over time, you have to do an integral to calculate work. So this now becomes the integral from x initial to x final. Those are just two positions, the one we start at and the one we end at. And inside the integral, we have f of x, so that's the variable force, dx. Okay, so again, this is the formula we would use for a variable force. Now, what's an example of a variable force? Well, the spring force, which is described by Hooke's law. And Hooke's law tells us that the spring force is minus k times x. What that's telling us is the more you stretch the spring out, the larger x is, the larger the force will be. And the negative sign tells us it's a restoring force. It tends to bring the spring back to equilibrium. And k in this is just a constant. Okay, so that's how we calculate work. So the next issue is kinetic energy. So kinetic energy is the energy associated with motion. So an object or a system has kinetic energy by virtue of the motion of its parts. So what's the formula for kinetic energy? Well, it's 1/2 mv squared. And if we take a look at the units, the SI units of this, we have a mass, which would be measured in kilograms, and then we have a speed, which would be measured in meters per second. But we square that, so we have kilograms, meters per second, all squared, which is equivalent to a joule. So the SI unit of energy is a joule. And so if we take these ideas of work and kinetic energy and put them together, we have the work-energy theorem. So what does the work-energy theorem say? We'll start with a statement in words, and then we'll write down an equation. The work-energy theorem says that the net work done by all forces acting on an object will equal the object's change in kinetic energy. Okay, so as a simple equation, we can write W net, the net work done on the object, is equal to delta K, the change in kinetic energy of that object. So the next thing to address here is power. So in physics, when we talk about power, we're talking about the rate at which work is done. So to go back to this example of pulling a box across the floor, if we pull it very slowly, then the rate at which we're performing the work is very slow, so there's low power. If we pull it very quickly, then the rate at which we're performing the work is very large, and there's a large amount of power associated with that. So if we just take this definition at face value, we would say that P for power is dW dt. It's just the time rate of change, basically, of work. But we also found that there's another very useful formula for power, which is F dot V. So if we take force and dot it with velocity, that gives us another way of calculating power. Now, what are the SI units here? The SI units are watts. And a watt is equivalent to a joule per second, because it's an energy unit divided by a time unit. Okay? And so that brings us to chapter 8, which is about conservation of energy. And the first topic that we touched on in this chapter was potential energy. Now, let's contrast it with kinetic energy. Kinetic energy is all about motion, whereas potential energy depends on position. So it doesn't matter how fast things are moving, it just matters where they're located as far as potential energy is concerned. And one thing that we learned about potential energy is that if we have a 1D conservative force, so the force only depends on x rather than like x, y, and z, for instance, then that force relates to the potential energy in the following way. The force is just minus du dx. And actually, we can interpret that graphically, if you remember. If we make a plot of the potential energy, where we have ux on this axis, and then we have x, the position on this axis, this can have any general shape that you want. But what we're saying is, if we take the derivative or the slope of this graph, then we get the force. But there's a negative sign in there as well. So what we say is the force is equal to the negative of the slope of the u of x versus X graph. Okay, so we can use the potential energy to say something about the force. Okay, so what were some examples of potential energy functions U of X that we derived? Well, first one was for gravity. Specifically for gravity near Earth's surface, what we have is the potential energy. It's a function of height, it's a function of y, is equal to m times g times y. We also saw that in a more general situation, so the gravity in general between two masses is given by the following. Ug is a function of r equals minus g m1 m2 divided by r. So the picture we should have is you have a mass m1, you have a mass m2, r is the distance between them, and so the potential energy in this situation just depends on the two masses, m1 and m2, and the distance r. Okay, so we only use this formula when you're close to Earth's surface. This one applies more generally. That's the idea. Okay, and then the last one was spring potential energy. So the idea here is if you compress or stretch out a spring, it will store some potential energy, and that's going to be given by, so US as a function of x, where x is the amount of stretching or compression of the spring, equals 1/2 times kx squared. Okay, so that's potential energy. Now, when we talk about the mechanical energy of a system, and we give, this is given by E, by the way. So the mechanical energy is the sum total of all kinetic and potential energies in a system. So it depends on the specific system you're looking at, but if you add up all the kinetic and potential energies in that system, you have what's called the mechanical energy. So in other words, E is just equal to K plus U. And this is an important concept because under certain circumstances, mechanical energy can be conserved. So if there are no non-conservative forces doing work on the system, and for example, friction would be an example of a non-conservative force. So if we don't have that, mechanical energy is conserved. In which case we can say E initial is equal to E final. Doesn't change. On the other hand, if there are non-conservative forces, if there are non-conservative forces doing work, mechanical energy will not be conserved. And in this case, if we want to analyze what's going on, what we would do is we would say the work done by these non-conservative forces is equal to delta K, change in kinetic energy, plus delta U, change in potential energy. So when you use energy methods to solve a problem, the first thing you should be thinking of is, do I have non-conservative forces like friction that I need to account for? If not, then I can use conservation of mechanical energy. If I do have these non-conservative forces to deal with, then I use W and C equals delta K plus delta U. Okay, so the last thing to say here is, just because mechanical energy can change, it doesn't mean that energy on the whole is not conserved, okay? It's just that when we have things like friction and air resistance doing work, the lost mechanical energy gets converted into things like heat and sound and other things. So energy is not actually disappearing, it just gets converted to things that aren't mechanical energy. So next we move on to chapter 9, which is all about linear momentum. So we'll start with the definition. What is momentum in the first place? Well, momentum basically quantifies how difficult it would be to bring an object to a stop. So, of course, the more momentum an object has, the more force you would have to apply in order to slow it down and bring it to a stop. That's the idea. So the definition in terms of an equation is P equals mv. You just take the mass of an object and multiply by its velocity, and you get its momentum. But it's really important to remember that this is a vector. Okay, things are going to go horribly wrong if you don't account for the fact that momentum is a vector and it has a direction. Okay? So that's the definition of momentum. Now, what we did in this chapter is we started thinking about a system of particles. So rather than just a single particle that's moving around, we can have any number of them that we keep track of together as a system. And what we found is, one of the important derivations we did in this chapter is that the net external force acting on that system, so we sum up all the outside forces acting on the system, and what we get is dp dt, the time rate of change of the total momentum of that system. And so this leads us directly to an idea called conservation of momentum, because if there is zero net external force acting on a system, then the total momentum of that system is conserved. Okay, so this is the idea of conservation of momentum. And we typically just write this as P initial equals P final. The total momentum of the system in the initial state equals the total momentum in the final state. And we can use this idea, for example, to understand what happens during a collision. If we have a collision between two objects, before they collide, they might be moving in a certain way. That's our initial state. After they collide, they might be moving in different directions with different speeds. That's our final state. We can relate what's going on in the initial and the final state using conservation of momentum. Okay, so another important concept that we came across in this chapter is the idea of center of mass. So the center of mass is basically the average position of all the masses in a given system. And we take the position of the center of mass to be it's given by the following formula. So RCM denotes the position of the center of mass. That's 1 over capital M, where capital M is the total mass of the system. And then times the sum from I equals 1 to n. So we're summing over all of the particles in the system, m sub I times r sub I, so mass times position. Now, we also have a way of writing this in integral form, which is 1 divided by big M times the integral of r dm. So this would be the integral form. And we would use that if we don't have a bunch of particles, but rather a solid object where we want to calculate the center of mass. So the picture you should have in your mind here is we have our x, our y, and our z-axis. We have our system of particles, so there are a bunch of particles scattered throughout. So we put a little boundary around that and say that's our system. So of course, each one of these particles has its own unique position, but there's some sort of average that we could talk about, which is the center of mass. So that x marks the center of mass. And what we're saying is we can calculate the position of the center of mass. We can actually say where the center of mass is located, RCM, by doing this calculation. And so as we'll see in the next chapter, this idea of center of mass keeps coming back. It's an important aspect of rotation. And that takes us to chapter 10, which is all about rotational motion. Okay, so the first topic to touch on here is angular kinematics. So kinematics, if you remember, refers to a description of motion. So we need to nail down some of the basic definitions in order to describe how something can rotate. So if we have an object that's able to rotate, there is an axis of rotation. That's the point where the object rotates around. And we can keep track of the orientation of the object using an angle, which I'll call theta here. So theta is what we call the angular position of the object. Now, if the object is not rotating, the angular position is constant. It doesn't change over time. But if the object is rotating, let's say in this direction, then the angular position will be changing. And what you'll have is what's called the angular velocity. So the angular velocity is given by omega, and it's defined as the time rate of change of angular position, or the derivative of angular position with respect to time. And if something is spinning at a constant speed, then omega will be constant, but if the rotation is speeding up or slowing down, then you'll have what's called angular acceleration. So if there's a change in the angular velocity, you'll have angular acceleration. This is given by alpha. And the definition of alpha is d omega dt, so the derivative of angular velocity with respect to time, or we can think of it as the second derivative of angular position with respect to time. So this should all match with the kinematic definitions that you learned back in Physics 44, except now we're dealing with rotation. Now, alongside these definitions are what we call the kinematic equations. So we have angular kinematic equations. And keep in mind that these only apply for constant angular acceleration. So only if alpha is constant can we use these equations. So the first one is theta equals theta naught plus omega naught times time plus 1/2 times alpha times time squared. So where you see a little zero subscript, that's referring to an initial value. So what this is saying is we can calculate the final angular position theta if we take the initial theta naught plus omega naught times time plus 1/2 alpha times t squared. Okay, another kinematic equation we have is omega equals omega naught plus alpha t. And then finally we have omega squared equals omega naught squared plus 2 times alpha theta minus theta naught. So these are the angular kinematic equations, and again, they only apply if alpha, the angular acceleration, is constant. Okay, so now let's move on to what we call rotational dynamics rather than kinematics. Let's start to think about the forces and the torques that actually put something in motion. So if we have a rigid object, okay, an object that just maintains its shape as it rotates, well, there are two ways it can move. It can both translate and rotate. And in general, we'll have to think about both types of motion. So the translational motion is governed by the following equation. We have the net force external equaling the mass of the object times the acceleration of the center of mass of the object. Whereas rotation is governed by the net external torque on an object is equal to I, that's called the moment of inertia, times alpha, which is the angular acceleration defined earlier. Now, keep in mind that these are both just different versions of Newton's second law. But we have a version for translation and a version for rotation to generally describe a rigid object. Okay, so first of all, let's define torque, because torque appears in the rotational version of Newton's second law. Torque is the rotational analog of force. So force we can think of as something you need to apply to an object in order to get it to start moving. Torque is what you would need to apply to an object in order to get it to start rotating. Okay? And torque, tau, is given by R cross F. So it's a cross product of two vectors. Now let's visualize what those two vectors look like. So here we have the axis of rotation for our rigid object, and then we have some point on the object where the force is applied. And we can have that force going in any particular direction. The R vector goes from the axis to that point where the force is being applied. And we can note that there's an angle between those, which we'll call theta. Okay? So the magnitude of a torque, and actually you can use this for any cross product, the magnitude would be the magnitude of the first vector, which is R, the magnitude of the second vector, which is F, and then sine of the angle between them. There's also a direction associated with the torque. It is a vector quantity after all. And the direction you can determine by the right-hand rule. So I'd like to show you a quick example just to remind you how cross products work and how we can use the right-hand rule to figure out the direction of a cross product. Okay? So I have two vectors here, A and B, and they both lie in the plane of the board. So if I take the cross product between them, I'm always going to get a vector that's perpendicular to both of these vectors. So it's going to be perpendicular to the plane of the board. Basically, it's either going to be out of the board or going into the board. Those are the two options. We basically just use the right-hand rule to figure out which of those two options is the correct one. So here's how it goes. We take the first vector, which is A, and we point the fingers of our right hand in the direction of that first vector. And then we curl those same fingers in the direction of the second vector, which is B, leaving your thumb pointing out of the board. So in this case, we determined using the right-hand rule that A cross B is out of the board. Okay, so that's how it works. Now, another term in this equation we have is I, the moment of inertia. So let's remember what this is all about. Moment of inertia is the rotational analog of mass. Because if we look at the usual version of Newton's second law, F equals ma, mass is basically telling us how resistant an object is to being accelerated. The more mass it has, the more difficult it is to accelerate it, the more force you need to accelerate it. So moment of inertia is a similar idea because the greater the moment of inertia, the more difficult it is to give it angular acceleration, to get it to start rotating. So the definition of I is the following. If we have a system of particles, then the moment of inertia of that system would be the sum from I equals 1 to n of m sub I times r sub I squared. Okay, and just as we showed in this picture, r is the distance from the axis of rotation. We also can put this in integral form, which is what we would use if we had a solid object and not just a collection of particles. This would be r squared times dm. And this is typically what we use when we deal with moments of inertia. Okay, so not only can we bring Newton's laws of motion into this picture of rotation, but we can also talk about energy. A rotating object has kinetic energy. And that rotational kinetic energy is given by K rotation equals 1/2 times I times omega squared. So we just need to know I, the moment of inertia, and omega, the speed of its rotation, to get rotational kinetic energy. Okay, so oftentimes we're going to be dealing with objects that rotate and translate at the same time. And a classic example of that is a rolling object. So when an object rolls without slipping, so for example, a ball rolling along the floor, of course it will be rotating, but at the same time it will be translating, and what we mean by that is the center of mass is moving with some velocity. So if an object is rolling without slipping, we have the following relationships called the no-slip conditions. The first one is the speed of the center of mass, so the magnitude of the velocity of the center of mass, equals the radius of the rolling object times the magnitude of omega. Also, the acceleration of the center of mass equals the radius of the object times the angular acceleration. And just keep in mind, these are relationships between the magnitudes of these vectors. So the directions, or whether things have a positive or negative sign, will depend on the situation. So the next chapter that we covered was chapter 12, which dealt with static equilibrium. And this was a pretty short chapter. We got through it all in just one day, but there are some important things to highlight from this chapter. The first being the center of gravity. So the center of gravity of an object is a single point on that object where we can consider the entire force of gravity to be acting. And this is an important thing to know because, for example, if you want to know the torque due to gravity acting on an object, let's say you have a beam and you attach it to a pivot like this, you need to know where the center of gravity is, CG, in order to know the torque acting on the beam. So that's the idea. what we found is that the center of gravity is basically the same as the center of mass. Now, there are some subtle differences between the center of gravity and the center of mass, but for an everyday sized object, it really doesn't matter. These are effectively the same thing. So, in other words, we can treat it as if the entire force of gravity is acting at the center of mass of an object. Okay, that's the idea. So that takes us to static equilibrium. If we have a system in static equilibrium, what we mean is there's no motion whatsoever. So a system would be in static equilibrium if it doesn't rotate or translate. And often, if you're building a structure, you're trying to design it so that it's always in static equilibrium. So what are the conditions that have to be met? Well, the first is, if we take all of the external forces and add them together, they should add to zero. That ensures that there's no translation. And also, if we take all the external torques acting on the system, those should also add to zero. And by the way, for this torque condition, we can use any pivot point that we want, and it will still hold true. Because if your system is really in static equilibrium, then if you calculate the torque about any pivot point, it's going to have to add to zero when you consider all the external torques acting on the system. Okay. The next chapter we covered is chapter 11, angular momentum. And of course, angular momentum is the rotational equivalent, the rotational analog of linear momentum. So in chapter 10, chapter 11, and chapter 12, basically we've built up a bunch of different quantities that apply to rotation that are sort of a mirror image of what we've seen for translation. So angular momentum is just another one of those, okay? So when it comes to angular momentum, there are a few formulas we need to remember. For a single particle, the angular momentum given by L, vector L, is R cross P. And here's the picture you should have in your mind as far as that goes. If we have some kind of coordinate system like this, and this is your particle, and this is its linear momentum P, the R vector is just its position. So you go from the origin of the coordinate system to the location of that particle, and if you take R cross P, you get the angular momentum of that particle. Okay, so we don't just want to know how to calculate the angular momentum of a particle, we also want to do it for a solid object. So for a solid symmetric object, angular momentum is given by L equals I times omega, where omega is the angular velocity of that object. So for example, if we have a cone that's spinning around like this, that's how we would calculate its angular momentum. Just take the moment of inertia I times the angular velocity omega. Okay, so one really important result that we derived in this chapter is that for a system of particles, the net external torque acting on that system is equal to dl dt, which is the time derivative of the angular momentum of that system. So if we think about what happens when there is zero net external torque, so if there is zero net external torque acting on a system, that means, well, the left-hand side of the equation is equal to 0. And so the right-hand side also must be equal to 0. In other words, dl dt is equal to 0, meaning L is not changing over time. It's just constant. In other words, if there's 0 net external torque acting on a system, its total angular momentum is conserved. Okay, that's the idea of conservation of angular momentum. Angular momentum will be conserved as long as you don't have any outside torques acting on a system. And the way we typically write this is just to say that L initial, the total angular momentum in some initial state, is equal to L final. Okay? Now, let's take more of a conceptual look at this idea of conservation of angular momentum. And in particular, let's think of a really simple system where we just have two masses which are connected by some sort of rod, and they're spinning around like this. So let's call this omega initial, the initial speed of that rotation. And then we'll imagine that sometime later, we bring the masses closer together as they continue to spin like this. And now they're spinning at some rate omega final. Well, what we see here is that the moment of inertia in the final state is actually less than the moment of inertia in the initial state because we're bringing the masses closer in. But as a result of that, it's going to be spinning faster. Omega final is going to be greater than omega initial, in other words, once we bring the masses in. That's just a consequence of conservation of angular momentum, because I times omega stays the same. In other words, the angular momentum is conserved. If we decrease the moment of inertia, we'll increase the speed of rotation in order to conserve angular momentum. Okay, that's just one conceptual example of this happening. So next, we covered chapter 14, which is about oscillations. And there's a really important type of system that we studied in this chapter called a simple harmonic oscillator. So a simple harmonic oscillator, or SHO for short, has the following properties. It has an equilibrium position. So this is the point where the force goes to 0. If you take it away from equilibrium, there will be something called a restoring force, which would bring it back to equilibrium. And the assumption when we talk about simple harmonic oscillators is that there's no energy loss. So in other words, no friction of any kind. Okay? And the classic example, the one we sort of went to the most in this chapter, was the mass spring system. Which basically consists of a mass and a spring, which are connected to each other. Let's draw that a little better. So here's the spring. Spring constant is K. Here's the mass, M. And the spring definitely has an equilibrium position where the force is equal to 0. But if we displace the spring from equilibrium, maybe we stretch it out or compress it and then let it go, what's going to happen is it will oscillate back and forth. So we can keep track of the motion of this mass using the x-axis, where x equals 0 is equilibrium. And so basically it's just going to oscillate around that equilibrium position. And what we found is the general solution for the motion, x as a function of time, is a times cosine omega t plus phi, where a is what we call the amplitude of the motion. That's the maximum displacement from equilibrium. Okay. Omega is what we call the angular frequency. Omega tells us how fast this thing is oscillating. So for a mass spring system, omega is going to be given by the square root of k over m. And this thing phi is called our phase. And that just allows us to match the initial conditions of the motion. Now here's an important point. All simple harmonic oscillators have the same general solution. Okay, in other words, doesn't matter if we're talking about a mass spring system or a different type of simple harmonic oscillator, the general solution for the motion is going to look like this. The only difference is the omega might be given by a different equation. So to give you some other examples, we had the simple pendulum, which is just a mass connected to a string that swings back and forth like this. Omega for a simple pendulum is given by the square root of g over L, but again, it has the same general solution, just a different formula for omega. Another example we saw was called a torsional pendulum, which consists of a twisting wire. And for a torsional pendulum, omega is given by the square root of k divided by I. So here's the torsional pendulum, just a twisting wire, which is connected to some kind of mass, and the wire twists back and forth. Again, that's just another simple harmonic oscillator. Okay, the last thing to say here is that for a simple harmonic oscillator, the time it takes to complete one cycle of oscillation, that's called the period. And t is what we use for the period. That's equal to 2 pi divided by omega. Okay, so what we've been talking about so far are simple harmonic oscillators where there is no friction of any kind, and once you set them in motion, they just sort of oscillate forever without losing energy. And that's not very realistic. In the real world, any system that you put in motion is going to be slowed down due to things like air resistance and friction. So what we want to do next is we want to allow for damping. So what happens if we allow for damping, which just means energy loss via friction? Well, basically what happens then is the amplitude decreases over time. So the size of the oscillations gets smaller over time. So rather than being a constant, the amplitude is a function of time, which is equal to A naught. That would be the initial amplitude times e to the minus gamma t, where this thing gamma is called the damping coefficient. Now, damping changes the frequency as well. It slows down the oscillations in general. And so the formula we derived to describe how damping changes the frequency is omega prime, that's the frequency with damping, this is equal to the square root of omega naught squared minus gamma squared, where omega naught is the frequency without damping, and gamma is what we call the damping coefficient. So then we went to chapter 13, which is about fluids. And some of the basic features of fluids that we need to remember are things like density, where density is the mass per unit volume of fluid. And density is given by the Greek letter rho, and this is mass over volume. And density appears in many of the equations of fluid statics and fluid dynamics, so that's just something we need to know about. Also, pressure. Pressure is the force per unit area exerted by a fluid. So the picture you should have in your mind is if we have some area, there will be a force from the fluid pushing on it. And if we simply take the ratio of that force divided by the area, we'll then have the pressure. So pressure is F divided by A. So one important fact about pressure is that if we have an incompressible fluid, and remember, incompressible means you can't compress it, you can't change the density, in other words. So density is constant. In this case, pressure is going to increase with depth. According to the equation, P, the pressure of the fluid, is equal to P surface, the pressure at the top surface of that fluid, plus rho GD. So in other words, if you have a container full of, let's say, water, and you know what the pressure here is at the top surface of the water, you can then calculate what the pressure will be down here, some depth below the surface, using this formula. Okay, the next thing we want to talk about is buoyancy. Okay, so buoyancy is the upward force felt by an object immersed in a fluid. And we have Archimedes' Principle to tell us how buoyancy actually works. So Archimedes' Principle says that the buoyant force is equal to the weight of the fluid which is displaced by the object. So if the buoyant force B is equal to the weight of fluid displaced by an object, remember, the weight is just equal to the mass of displaced fluid times G. But mass is just density times volume, according to the definition of density up here. So this would also be equal to the density of the fluid times the volume of fluid we displace by having the object in the fluid times g. That's how we calculate the buoyant force. Okay, so the next thing is how do we deal with moving fluids? Okay, fluids that are actually flowing rather than just standing still. So the flow of an ideal fluid, when we talk about an ideal fluid, among other things, we're assuming no viscosity, so no energy loss through viscosity, and a number of other assumptions. But if we have an ideal fluid, the flow will be governed by a set of two equations. So the first equation is the equation of continuity. Okay? And the equation of continuity says that the flow rate, so this is what we call R, the flow rate, which is the volume per unit time flowing through a given area. This flow rate is equal to the cross-sectional area A times the speed V. And the equation of continuity basically says that this flow rate is constant. So what we can say is for any 2 points in the fluid, A1 V1 equals A2 V2. Okay, so the classic example where the equation of continuity applies is if you have a pipe where the cross-sectional area of that pipe changes, maybe it gets narrower, something like this. So the speed of the fluid over here and the speed of the fluid over here are going to be different because of that changing cross-sectional area, but you can relate them using the equation of continuity. Okay, we also have Bernoulli's equation. So Bernoulli's equation tells us that there's another quantity that stays constant in an ideal fluid, which is pressure plus 1/2 times density times the speed squared plus density times g times height. That whole thing is constant. So like before, we can take any 2 points in the fluid and say that P1 plus 1/2 times rho times V1 squared plus rho times g times y1 equals P2 plus 1/2 times rho times V2 squared plus rho times g times y2. That's typically how we use Bernoulli's equation. And that takes us to chapter 17. In chapter 17, we covered thermal expansion. So the idea here is that most materials will expand when heated and contract to a smaller size if they're cooled down. Okay, that's the concept of thermal expansion. Now, there are sort of three different ways to look at this. We have linear expansion, area expansion, and volume expansion. So if we start with linear expansion, we're talking about the change in length, or delta L, of an object, which would be L minus L naught. So the final length minus the initial length. This is equal to alpha times L naught times delta T. So here, let's label all of these terms. L, that's the final length. L naught, it's the initial length. Alpha is what we call the coefficient of linear expansion. And that's going to just depend on the material. Every material has a different value of alpha. And then finally, delta T is the change in temperature. Okay, so that's how we describe a change in length. But we can just as easily describe a change in area. And area expansion is given by delta A, which would be A minus A naught, using the same notation as before. This is approximately equal to 2 times alpha times A naught times delta T. And then finally, we have volume expansion. So delta V would be some sort of change in volume that happens as a result of a change in temperature. Delta V is V minus V naught, which is approximately equal to 3 times alpha times V naught times delta T. And that's basically everything we learned in chapter 17. And the last chapter that we covered was chapter 19, which is about heat and temperature. So you can think of this as your introduction to thermodynamics, which if you take Physics 47, we're going to go into a lot more detail on. And the first thing we talked about was the ideal gas law. So if you have a gas, there's a relationship between pressure, volume, and temperature, which is given by PV equals N times KB times T. So P is the pressure, V is the volume, N is the number of particles, number of particles of gas in your particular sample, KB is just a constant, and T is the temperature. And using this law, what we proved is, for an ideal gas, we proved that K bar, which is the average kinetic energy of the gas molecules, that's equal to 3/2 times KB times T. And this gives us a microscopic interpretation of what temperature is. So in particular, the average kinetic energy of the molecules that make up a system, or let's just say the particles that make up a system, is directly proportional to its temperature. So if the temperature is raised, if you heat something up, what you're doing on the microscopic level is increasing the kinetic energy of the molecules that make it up. When you heat something up, the molecules jiggle around faster than they did before. You cool something off, you lower its temperature, and those molecules are now moving slower than they did before. That's the idea. That's what temperature really is on a microscopic level. So the next thing to define is heat. So heat is simply when energy flows from hot to cold. So if energy flows from a hot region to a cold region, we just call that heat. And the picture to have in mind is, let's say you have a hot region TH and a cold region with temperature TC. If you allow those two regions to exchange energy, if you put them in contact with each other, then you're going to have heat flowing from the hot region to the cold region. We call that heat Q, by the way. And heat will continue to flow until, so heat flows until thermal equilibrium is reached. And that means the two regions now have the same temperature. Okay? So when we talk about the specific heat of a particular substance, specific heat is the heat required to change the temperature of 1 kilogram of a substance by 1 degree Celsius or 1 Kelvin. So basically, the larger the specific heat of a substance, the harder it is to change its temperature. Okay? So if we have a temperature change happening, we'll have the formula Q equals mc delta T to describe that. In other words, if you take the mass times the specific heat, that's what lowercase c is, times the temperature change, that gives you the energy or the heat that needs to flow into that material to achieve that temperature change. Now, we also have what's called the latent heat. So latent heat is the heat required to change the phase of 1 kilogram of a substance. So for example, melting or boiling are examples of phase changes. So it takes heat, Q, in order for a phase change to happen. Q is given by plus or minus m times L, that's the latent heat, for a phase change. And the other thing to keep in mind is that phase changes happen at constant temperature. So let's say we have ice. The phase change from solid to liquid occurs at 0 degrees Celsius. If we have liquid water, the phase change from liquid to gas, when we boil the water, happens at 100 degrees Celsius. Okay, so we can put these ideas together to solve certain types of problems where if a system is insulated, if a system is well insulated, it won't exchange heat with its environment. And therefore, we can say Q total for that system is equal to 0. So just to sketch out an example, let's say we have two objects, 1 and 2, And if that's our entire system, when we say Q total is equal to 0, we just mean no heat flows in or out of the system. So if we say T1 is bigger than T2, for example, when we talk about the total heat, that would be Q1 plus Q2 equaling 0. But there's going to be a heat loss from the first object because it's at a higher temperature. There's going to be a heat gain by the second object. But when we take those two heats, one of them negative, the other positive, and we add them together, we get 0 because, again, no heat is flowing in or out of the system. So that's the idea behind problems like this. Now, when it comes to heat, there are different modes of heat transfer. We talked about convection, radiation, and conduction, but conduction is the one that we'll really focus on. So conduction is how heat typically flows through a solid material. And what we saw in lecture is a formula for the rate of heat conduction. In other words, delta Q over delta T. This is given by K times A times delta T over delta X, where K is what we call the thermal conductivity of a given material. The picture you should have in your head is something like this. So imagine a slab of material. A is the area. Delta X is the thickness. On one side of the material, the temperature is high. On the other side of the material, the temperature is lower, so we know that heat flows from hot to cold, right? So heat is going to be flowing through that material from the hot side to the cold side. That's going to be our delta Q. So what this is saying is the heat flowing through the material per unit time, that's delta Q over delta T, that equals K, the thermal conductivity of the material, times A, that's the area, times delta T, that's just the temperature difference between the hot and the cold side, TH minus TC, divided by delta X, the thickness of the material. And that's basically everything we covered this semester. So I want to leave you with some final thoughts before we end the semester. And I really want to zoom out and look at the big picture of the last year of physics that you've taken in Physics 44 and Physics 45. What we've basically been doing in these two courses is we've learned how to use the laws of physics to make predictions. And what do I mean by make predictions? We're making predictions of how a system that we're looking at, whatever that system happens to be, we're looking at how the system will move in the future. And the basic picture of that is we know what the system looks like in some initial state. We know how it starts off. We plug that information into some type of physical law. And this could be anything from Newton's second law to conservation of energy to conservation of momentum, some sort of principle of physics that we're using. And what comes out of that calculation is a prediction about what the final state of the system is going to be. So in a very real sense, this is a way of predicting the future. And so far, we've just been using this for relatively simple systems like a ball rolling down a ramp or a pendulum swinging back and forth. But in principle, you could really use this sort of basic idea for anything to predict how a physical system is going to behave sometime in the future. So a question naturally arises. Can you actually just use the laws of physics to predict any future event whatsoever? And the answer is actually no. There are some reasons why we can never perfectly predict the future. And there are two things I want to highlight. Both of these lie beyond the scope of Physics 45, but I think they're really cool ideas that I encourage you to read about if you're interested in this sort of thing. So the first is chaos. So in complex systems that have a lot of different moving parts that interact with each other, there can be what's called chaotic behavior, where a very small error in the measurement of the initial state can lead to a very big error in your calculation of the final state. Okay, this is called extreme sensitivity to initial conditions. It's a feature of what we call a chaotic system, where if you get the initial state even slightly wrong, your calculation of the final state is just going to be garbage because there's such a large error in it. And that means we don't really have that much power to predict the future if a system is chaotic. Okay, there are some fundamental limitations to how well we can predict the future behavior of a system if that system is chaotic. There's also quantum mechanics. So in the laws of physics that we've learned about up until this point, basically Newtonian physics, everything is perfectly deterministic, right? If you plug in an initial state, you're going to get some definite final state out of that calculation. But in quantum mechanics, particularly on the microscopic level, there just are some phenomena, some things that happen, that are inherently random. And they actually can't be predicted. The outcome is just random. There's no way of calculating what the outcome will be. So because there's some fundamental randomness in the laws of physics, at least at the small scale, we can't perfectly predict the future of every single thing that happens, okay? So anyway, this is just some food for thought, things to think about beyond Physics 45. So we're going to end it here, and we're going to end the semester here. So it's really been a pleasure to get to know all of you, even if it's been remote. And I hope you're all doing well. Good luck on your finals, and take care. I'll see you later.